Okay, so I think we have gathered enough information regarding the random process, and now probably we are almost ready towards utilizing this means understanding of random process towards doing the noise analysis of some of the systems which we have already discussed. So, I will first give an outline of the basis of our noise analysis, means how we wish to do that, what is the measurable quantity, how do we really characterize a particular modulation scheme in terms of noise analysis. So, what we will do whenever you are trying to modulate something, we will try to see if we means we have not employed that modulation, that means the original data which is in baseband, if we would have directly transmitted it and in the receiver just with a low pass filter, if we would have received that. So, what could have been the signal to noise ratio, that we will try to measure first. So, basically our that we will call as a reference signal to noise ratio. Okay. So, that reference signal to noise ratio, how we would like to compute, that is suppose I have a message signal MT which might be a voice signal, let us say it is of course, it is a band limited signal. So, it goes from minus W to plus W. So, that is the message signal, that is the frequency response of that message signal. We also know that the power of the overall signal, that is actually minus W to plus W, if the corresponding power spectral density, let us say that is SF or SMF, this if we integrate we get the power P. So, this is something we know, that is the overall power. So, this is already given that this is the overall power of the message signal, that will be means received at the receiver. Okay. So, I am not saying that that will be transmitted, or we are saying that in the channel there is no attenuation, let us say. So, either it is transmitted with this amount of power or there is some attenuation. So, just at the beginning of the receiver or at the antenna of the receiver, this is the power that we will be getting, okay, if we just transmit this signal. All right. So, either way you can take assumption. So, the very clear cut assumption is we are not means modeling the attenuation that is being created or power dissipation that is being created by the channel. Okay. So, that is something we are not, because here we are just interested in channel noise, not the attenuation. Okay. So, we will take that assumption that whatever is transmitted, that will be received at the receiver. So, this is the power that will be if in the baseband directly I transmit the signal without any modulation. So, that should be the power which will be launched at the transmitter and that will be received. Okay. And this corresponding signal is band limited. So, what we should employ, the best thing we have already talked about AWG and noise. So, we will say that in the channel probably AWG and noise will be added. Okay. So, it is a white noise. So, the spectrum is flat and it looks like this with a strength eta 0 by 2. Okay. So, that is the power spectral density of noise, PSD of the noise signal, let us say that is NT. Okay. So, this is something we know already, the noise characteristics, and we also know that the noise follows Gaussian statistics. That means, at a particular time you sample from the entire ensemble of noise signal that are possible, and then if you plot the histogram with normalization, you will get a Gaussian PDF. Okay. And this noise will be in the channel added to the signal, that is also something we know, that is why we have called it additive white Gaussian noise. Okay. So, in the channel what will happen, if I transmit this MT at the receiver, because we have no attenuation. So, MT will be intact at the receiver plus the noise signal NT will be added, that should be my signal that is received. Okay. So, let us call that as let us say WT. Okay. So, this is what will be received by the receiver. Now, what do I want to do? It is a low pass equivalent signal. We have already told that if it is a low pass signal, I am only interested about the message. If I allow the entire band to come, of course, my message will come and nothing else we are transmitting, let us assume nothing else we are transmitting, but that entire noise power will actually come to the receiver. So, signal to noise ratio will be very high. Instead of that, we can just employ a low pass filter of bandwidth W, that minus W to plus W. If we do that, how much noise will be coming in? That will be from minus W to plus W if you integrate this. So, that should be 2W into N0 by 2. So, overall noise power should be N0 into W, 2 gets cancelled. So, this is the noise power Pn. Okay. So, this is what I will be receiving, out of which the noise power is this. The signal power I already know, because we have said it is not getting attenuated. So, that should be the signal power. So, overall we can say signal to noise ratio should be corresponding signal power divided by corresponding noise power. So, this is how we will be characterizing the system. If we just, this is the reference SINR or SNR, okay, when we transmit the signal raw in its raw form without any modulation. Okay. So, that should be the reference part. And then what we will do, we will also try to employ some modulation scheme. We do not know what modulation scheme. So, due to that there will be some signal ST which will be transmitted probably. Okay. So, it will be a modulated version of MT. So, if it is DSB-SC, it will be MT cos into cos 2 omega Ct. If it is SSB, then it will be MT cos omega Ct plus MHT, which is the Hilbert transform of MT into sin omega Ct, something like that, or either plus or minus. Okay. So, whatever the modulation scheme, I will be transmitting this. Okay. So, this is something we will be launching, and then at the receiver there will be some procedure, because what we wish to calculate is after the entire reception process, whatever signal we get, what is the power of it, and some spurious noise that will be also going through that receiver process, and due to that at the end there will be some noise power, and we have to take a ratio of these two. Okay. So, that will be the signal to noise ratio of the modulated signal. Okay. So, we modulate, we launch ST, and then at the receiver we receive it along with noise. So, signal this ST plus NT will be my input at the receiver, then receiver will do all its processing. If it is an error detector, it will do that. If there is a band pass filter, it will do that. If there is a low pass filter, if there is a mixer. So, all those things will be done equally with the signal as well as noise. So, that is something which we will have to carry through the entire experimentation. Okay. And after that we will try to see the message signal coming out as usual, but there will be also a noise part which will be coming out, which might be now a complicated noise signal, okay, because it will go through the receiver process. And then finally, we will try to evaluate the overall power of that noise, which will be after the reception, and the signal power that we will be getting after the reception. The ratio of that should be my, after modulation and demodulation, that should be my signal to noise ratio. Okay. So, this is the signal to noise ratio which we will be getting for a particular modulation scheme, and the signal to noise ratio for reference we have got, that is we do not do any modulation, just baseband we transmit. And what we will be trying to do is we will try to create a figure of merit of a modulation scheme. So, we call that FOM, figure of merit, that should be this SNR which is for that modulation scheme. So, for a particular modulation scheme divided by that SNR reference. Okay. So, whatever value we will be getting, if we are doing fair comparison, for everything we will try to see whether the SNR improves from its baseband or SNR decreases from its baseband. Okay. So, that is something we want to see. We want to see which modulation actually enhances the SNR performance or which modulation scheme actually decreases the SNR performance. So, that is why figure of merit has been introduced. But here there is something which we have not still talked about, that is the launched power. Okay. So, if we do not really equate the launch power for this reference signal as well as the modulated signal, then we are comparing something with some other thing. Okay. We are not doing a fair comparison because I can put any power in that particular modulated signal, and then if we wish to compare them, probably that something might be better. So, what we have to also ensure in this process, if we really wish to test it, we have to ensure that the power ST that is being launched, that must be equal to the power that we will be putting in the baseband. These two powers should be equated. Okay. So, then we know at the transmitter we are transmitting equal power, then it is going through the entire receiver process, and then finally for both the schemes, which is one is baseband transmission, because now the powers are equal. So, whatever noise is being added to this process, what is the figure of merit of the modulation. Okay. So, probably once we do the calculation, it will be very clear, but this is the methodology we will be applying or adopting towards analyzing this kind of system, okay, any of those system. Okay. So, let us try to see what we can do for a particular system. So, let us say we have a DSB-SC modulation, right. So, the first reference part will be, I will put this MT, right, and then this particular message signal will be transmitted. So, it will be transmitted. Okay. So, the message signal at its baseband I just transmitted. At the receiver, so this is the TX part, at the receiver what I will do, I will take this signal. Now, the signal will be contaminated with noise. So, it should be this MT plus some NT, and I know that it will be additive. So, it is plus always. Okay. So, that should be incident on my receiver. At the receiver I have a very simple technique, we have already talked about that it will just be a low pass filter having a bandwidth which is equivalent to the signal bandwidth. So, that should be minus W to plus W. Okay. So, that low pass filter will be, and that should be my output signal y t. So, this is my output. Okay. So, this is for the reference we will be doing. Next, I will put a modulated signal which is nothing but ST, which is equal to MT cos 2 pi FCT, right. So, this I will transmit, but while transmitting, so this is for the modulation, this is for DSB-SC. So, we are trying to now analyze the whole system for DSB-SC. Okay. So, whenever we are modulating, we need to ensure that this power and this power, both of them are launching equivalent power. So, this is something we will have to make sure. Okay. And then I will be receiving somewhere. So, this should be, now it should be ST plus NT, because ST has been transmitted and additive noise has been added to it. First thing we will do is, this is modulated. So, the frequency will be centered around omega c or Fc. Okay. So, I have to employ a band pass filter, because we have already told that whenever it is modulated, I want to take just my signal which is centered around omega c with a band of 2W, right. So, I want to also take just minimum amount of noise. So, therefore, I will put a band pass filter, so that just the minimum amount of noise which is centered around Fc and 2W bandwidth, that will be taken into account. So, I should be putting a band pass filter which is centered around Fc, which is exactly the modulating frequency, and bandwidth is 2W. Okay. So, that is the first thing we will be putting. So, this we call as, let us say, xt, okay, after passing through the band pass filter. Now, there will be first thing for DSB-SC, what do we do? We first put through a mixer, we will be multiplying by cos 2 omega ct, or sorry, cos omega ct or 2 pi FCT. So, we will just multiply by this, somehow we will do carrier synchronization, we are not talking about that part. Okay. So, this is just the simplest part where the carrier synchronization is differently done. Okay. It is not that Costa's receiver or some other thing. Okay. It is the simplest one where separately we do carrier synchronization, we are not bothered about that right now. So, with that I will get Vt which will be generated this we are calling as Wt. Okay. And then of course, whenever we multiply by cos 2 pi fct, there will be higher frequency term that will be created, which we have to filter out. So, we will be putting a low pass filter, that is actually the overall DSB-SC demodulation. So, a low pass filter which is again centered, means low pass filter which has a bandwidth of W, and that must be my Yt or output. Okay. Now, what is happening? This entire process, your noise also will go through this process. So, we will have to characterize it properly, that whole thing properly we have to characterize. The first process of this is equating these two power. Okay. So, let us try to see how do we do that. So, already we have said that my P is that is my P, right. We have already told that this is something we are assuming, that the overall signal power spectral density, if we integrate over the band of interest, that is the power we get. Okay. Now, whenever we modulate, okay, let us try to see what kind of power we will be getting, because we have to also launch similar amount of power. Okay. So, that is something we will have to do. Okay. So, let us try to see when we modulate what do we get. If we modulate, I will be getting this. So, that is the St which is Mt cos 2 pi fct, right. What will be the corresponding power spectral density? So, if this was SMF, after modulation we already know from the power spectral density and Fourier transform property that this will be just, if this was my SMF, this will be going towards plus Fc minus Fc with the same band of 2W, and the strength will be just half, right. So, basically the strength will be not half, it is 1 by 4, because MF becomes half and the square of that, because power spectral density will be mod square. So, it will be 1 by 4. So, this will be 1/4 of that whole thing and this will be 1/4, or overall if I integrate, this must be 1/4 of this thing. Okay. So, overall power of this one will be 1/4 of this. So, if this was P, that should be P by 2, this integration will give me P by 2, this integration will give me another P by 2, sorry P by 4, right. So, P by 4 over here, P by 4 over here, if you add that, so overall power should be P by 2. So, this is something we know, anywhere you multiply by a cosinusoidal or sinusoidal, you will be halving the power, overall power. Okay. So, immediately we know that the launch power should be P by 2, right. So, this is something we should be aware of. Okay. So, all right. So, this is something whatever is happening over here. Now, let us say for the baseband, can we analyze this? Okay. So, to be more specific or generalized, let us try to put this, instead of just putting Mt cos omega ct, let us try to put a factor into it. Okay. So, where there is an amplitude of this cos and there is a modulation factor, let us say that is C. So, that is within our hand and we will be equating the power. So, it does not matter, right. So, let us say instead of St writing as Mt cos omega ct, we write it as C AC Mt cos 2 pi fct. So, immediately what will be the power of it? The power of this signal, that must be, see Mt cos omega ct, that must be P by 2, and this, because it is power spectral density. So, it should be square of this. So, it should be that power should be P of S should be C square S square P by 2. So, that happens to be, if I try to transmit this particular signal, that happens to be the power. What we have said already, that this power must be also launched when we do baseband, that reference signal, because we have to equate these two power. We need to, in both the cases, we need to actually put the same power. So, we need to equate these two power. So, if this is PS, the same power has to be launched for baseband processing. So, we will be launching again, instead of launching this P power in the baseband, we will be launching this amount of power. So, which is C square SE square P by 2, this amount of power. So, accordingly we will amplify the signal, and whatever we need to do, we will do that. Okay. So, that the overall power becomes this. Okay. So, if this is the power, noise remains the same, right. So, what will be the noise power? Noise power will be whatever we have calculated. So, which was N0W. So, that is the noise power. So, therefore, what is the SNR reference? That should be this power divided by this noise power, already passing through a low pass filter. This noise power has been already evaluated, passing it through a low pass filter of bandwidth W. Okay. So, therefore, it should be C square SE square P divided by 2 N0 W. So, that is one part of our calculation. SNR reference has been evaluated. Okay. So, now let us try to do for the actual modulated signal, right. For actual modulated signal, we have drawn it. So, this must be my overall demodulation process, where ST is given by this, of course, a C into AC should be there. Okay. So, let us try to write that. So, my XT okay, so we will try to write that XT. XT is after passing the signal plus noise through a band pass filter. Okay, so, that is XT. What is XT? XT must have that ST and the noise which is passed through a band pass filter. In the last class, we have already characterized a band pass noise, right. We have told that a band pass noise must have a in phase component and a quadrature component. We have already characterized those things. Those are also random process, which has, we have also evaluated that they do not have any cross correlation, right. So, this is something we have already, and they are generally orthogonal to each other. Okay. So, this is something we have already stated. So, we know that noise must be now represented as in phase quadrature component. So, I can write that noise in terms of in phase and quadrature component. So, that is something which we have learned from the random process, band pass random process analysis. Okay. So, XT must be my signal, because signal through that band pass filter remains intact, because it is a band pass signal of that same band whichever I am putting. So, signal remains unchanged. So, that should be C AC cos 2 pi f c t into m t, that must be my signal, plus the noise which was N t, that was the overall noise. Now, it has passed through a band pass filter. So, I can write as N I t, which is the in phase part, into cos omega c t, which is the central frequency, or 2 pi f c t, which is the central frequency of the band pass filter, plus N q t, which is the quadrature component, into sin omega c t. We have already told that that is the representation we can get whenever we pass a white noise through a band limited or band pass filter, or a band pass noise can be represented as this. So, I have got this x t. Now, what will happen if I again go back to the circuit? X t gets multiplied with cos 2 pi f c t, right. So, what eventually is happening, my signal, not only the signal is getting multiplied by 2 cos 2 pi f c t, the noise also will be multiplied by that. So, we are actually in the process that additive noise we are taking through the receiver, and every step we are trying to see what is happening to the noise after doing that step. Okay. So, let us say that is V t, which is nothing but x t cos omega c t or 2 pi f c t, that must be this multiplied by cos 2 pi f c t. So, C A C cos square 2 pi f c t into m t plus n I t, again cos multiplied by cos. So, that should be cos square 2 pi f c t plus n q t cos 2 pi f c t into sin 2 pi f c t, right. So, this is something what we get. So, we get the overall expression after the multiplier. Okay. Now, what we will do? We will pass it through a low pass filter. First of all, let us try to see which are the higher frequency term. Okay. So, this cos square, if I just put a half C A C, so cos square will become 2 cos square. So, I can write it as 1 plus cos 2, 1 plus cos 4 pi f c t into m t, right. Similarly, I can write for this one also n I t 1 plus cos 4 pi f c t, and this is again half, this is 2 cos into sin. So, that should be sin n q t sin 4 pi f c t. Now, let us pass it through the last part of the receiver circuit is this low pass filter or bandwidth W. So, which are the component of this one? So, I have this component, this component, this component, this component and this component. Out of them, which are higher frequency term, which that low pass filter will reject? That must be rejected, because f c is much bigger than already W, and therefore, 2 f c must be even bigger than that W. So, that must be rejected. So, this must be rejected, this also must be rejected and this must be rejected. So, finally, after low pass filter, let us say this y t, it remains to be half C A C into m t, that is related to the message signal, plus the noise term which is half n I t, that is it. Okay. So, we are left with these two terms, which is very good for us, because the signal and noise term are clearly separated after the DSB-SC. So, all we have to now do is try to evaluate the power of this one and try to evaluate the power of this one, and take the ratio of these two, and then try to see how this is compared to the reference SINR. So, what we will do in the next class, we will just try to see this figure of merit of DSB-SC. Okay. Thank you.